All right, new question. Rate of reaction when a halogenoalkane, aqueous sodium hydroxide measured with different concentrations used. The results are shown in the table. Use these data. Very good, by the way, these data is a plural word, of course, to deduce how the concentration of each reaction affects the rate of reaction. Explain how you reach your conclusions. Now, there's quite a lot of these as we're going through. This was off Unit 2, so that's an AS question. So it's not asking for a hugely in-depth answer. You just need to compare a few things. So I'm going to compare experiments 1 and 2. What happens in experiments 1 and 2 are the OH stays the same. We double the halogenoalkane, right? So, and what does that do to the rate? Well, it goes from 1.2 to 2.4, both times 10 to the minus 5. So we doubled the rate. So double halogenoalkane, double the rate. We can say that the halogenoalkane is proportional to the rate. Now we've got to think about the OH minuses, so let's delve a little deeper. We now want to find something in which this value is the same and this value is different. And experiments 1 and 4 would seem to meet the bill there. As we go experiment 1 and 4, the halogenoalkane is the same. The OH, however, doubles from 0.1 to 0.2. And what happens to the rate? The rate stays the same. So in other words, the OH minus has no effect upon the rate of the reaction. So overall, the rate of the reaction proportional to the concentration of the halogenoalkane. As of course we would know later on, we will call it first order in the halogenoalkane and 0 order in the OH minus. But that's for A-level. Same kind of question, okay, except with a little twist to it. So we're doing a clock reaction. Iodide ions can be oxidized to iodine, reaction with acidified hydrogen peroxide. So there we go, there's the iodide, there's the acidified hydrogen peroxide, there's the iodine. Rate of reaction will be followed by a clock reaction by the appearance of a blue-black color. So of course, clock reaction, as you mix the solutions together, nothing happens, nothing happens, nothing happens, then boom, it changes color. And so an experiment carried out to determine the effect by varying the concentration of the iodide ions. So here's the iodide, 0.1, 0.2, 0.3, 0.4, 0.5. And we're looking at the time taken for the appearance of the blue-black color. And of course, as a good experimentalist, everything else kept constant. So the first thing is use the rate equals 1,000 over time to calculate the rate for each experiment, complete the table. So all we're going to do is just going to take each of these numbers in turn and divide them into 1,000. Okay, rate per second times 1,000. So 50, 56, 83, and 100. Okay, rather trivial, also rather annoying. Where does the 1,000 come from? Well, because it just looks cute and so forth. You can actually get a much better understanding of how clock reactions happen if you think about where does this rate happen. Rate is always change in an amount over time. Well, that's the over time, right? We're dividing by 56, 20, blah, blah, blah. But where does this 1,000 come from? Okay, so don't particularly like this sort of black box approach to this. But anyway, the rate is always going to be inversely proportional to time. So we're just multiplying by 1,000 for convenience in this case. So we had our table in which we calculated the rate against the concentration of iodide, and now it says plot it. So you had a nice little bit of graph paper on the exam paper when you did this. Those who did it in 2018 plotted the iodide. There was my rate per second that I calculated. Now, I've drawn a straight line through this. Don't particularly like drawing the straight line through it because when you look at this, it's more like a star constellation, isn't it, than any kind of nice straight line graph. But you never connect the dots. This is not a sales graph. It is a decent graph in which there should be a relationship between the two variables, the independent variable and the dependent variable, the concentration of iodide and the rate per second. And I feel fairly confident drawing this straight line here because I've got enough points below the line and points above the line to make me think that this is a decent straight line. And of course 0, 0 is a good particular point on this because if you hadn't got any iodide, you ain't going to get any rate of reaction. So anyway, looking at all this, I would have said that the relationship between the iodide and rate of reaction is that they are proportional. Now then we've got to use the graph to calculate the time the reaction would take to turn blue black using 0.15 moles per cubic decimeter of I minus. Well, 0.15 would be smack in the middle of 0.1 and 0.2, so we'll take that and draw it up here. Read along to get the rate, and that rate would be about 33 per second. Looking at where this was. Now, of course, it didn't want the rate, it wanted the time. Well, the way we got the rate, if you remember, was we took the time and divided it into 1,000. So the relationship between rate and time is 1,000. So in this particular case, the time is going to be that 1,000 divided by the rate, which is 29 seconds. For each experiment, rate was calculated using the time to produce excess iodine. Explain why this is only approximation for the rate as the reaction proceeds. And the answer is because it's just the average rate. Okay, when any reaction starts, it's going to go fast, and then of course as time goes on it slows down. Well, instead of us plotting that nice little curve of concentration against time, we're just saying we got nothing at time 0, we've got this particular concentration after time t, so the average is just the concentration change, in this case that 1,000, whatever that meant, divided by the time taken. Okay, only the average rate when you do a clock reaction like this. Many factors affect the rate of reaction. Explain what change concentration affects the rate of reaction. Changes the number of reacting particles. Some of these particles, the reacting particles, are involved in the slow step, which I don't think you talk about at AS, but we'll talk about it now, which requires collisions. And of course, as you have different number of particles, different numbers of collisions, you have more particles, more collisions, fewer particles, fewer collisions, so a different rate. Now we got another table. Certain conditions, nitrogen monoxide, NO, reacts with carbon monoxide, CO, and oxygen, O2. So a 3-reactant reaction. That's rather cool. To give NO2 and CO2, study the rate using varying initial concentrations of NO and oxygen. In other words, leaving the CO constant, gave the following data. Use these data to determine how the concentration of NO affects the rate of reaction. So in this case, here's our concentration of NO. We need to look at how it affects the rate. So I would look at experiment 1 and 2, because in 1 and 2 I changed the NO, but I left the O2 the same. And when I changed the NO, I doubled it. And the effect that had on the rate was to quadruple it, right? 4.4 to 17.6 is 4 times. So double this, quadruple that. That means that the rate is proportional to the NO squared. 2 squared, the doubling, is 4. Okay. Look at experiments 1 and 3 just to check ourselves. Again, oxygen staying the same. From 1 to 3 we are tripling concentration of NO. And as we look at the rate, we go from 4.4 to 39.6, which is multiplying it by 9. So as we triple, it becomes 9. How do we go from 3 to 9? We square it. So the rate again proportional to NO squared. So 2 sets of data there tell us that the rate is proportional to the NO concentration squared. Always double check your results if you can. All right, now blah blah blah, go to now same thing but concentration of O2. So in this case we got the same, and now we double it. So what we want to do is we want to find out, right, which I compare with experiment number 4. That means that the NO stay the same, but my O2 is doubled. And that is experiments 2 and 4. Same NO, doubling the O2. And what does that do to the rate? Absolutely nothing. Okay, so we double the O2, but the rate stays the same. In other words, there is no relationship between the rate and the concentration of O2. Fancy way to say that is to say it's proportional to concentration of O2 raised to the power of 0. O2 is a 0 in the rate of this reaction. Suggested method could be used to follow changes over time. Reaction of NO, CO and O2 proceeds. Explain your answer. Well, as mentioned previously in question 1, at the A level there's really only 3 things to consider. Are you going to have a color change? So one of the reactants or products is colored, in which case you can follow the change in color. Is there a gas situation involved, or is there pH, H plus and OH minus? Well, in this particular reaction, okay, NO2 is one of the products, and that's colored. It's sort of browny. So you go from colorless, and gradually the reaction goes a little bit pale brown, a bit darker. So you could follow the production of NO2 with its color. Or you can look at the gas. You start with 3 moles of gas on the left-hand side, 2 moles of gas on the right-hand side. So as the reaction proceeds, the volume of gas is going to diminish. And if you connect your whole system to a syringe that's already been pulled out to an extent, well then as the reaction proceeds and you're making fewer molecules of gas, you'll reduce the volume of gas, and the syringe volume would decrease. And so you can plot that decrease in volume against time to follow the fact that you've got 3 moles of gas going to 2. No pH change in this one, although arguably you could bubble the CO2 through and make an acidic solution and watch the pH there, but that's a little bit clumsy to do that. Reaction rates can be measured using a clock reaction. Data below show the results obtained by a student iodine clock experiment. The concentration of iodide ions was the only difference between them. So we had 0.2 iodide, 0.4 iodide. So the first thing is complete the table with the appropriate values of the mean time taken. So we'll take the mean of all of that, and it's 35. We're dumping out 46 because you go 35, 46, 36, 34, 46 is the anomalous value. Personally, I would have run this experiment quite a few more times to make sure I'm correct in dumping that, but under the A-level rules, dump that one because it is definitely not concordant, which is a horrible word, with the other values. No such problem here, 1817, 1817, given an average of 17.5 seconds. Calculate the rate of reaction for these two concentrations. Well, rate is 1 over the change in time. In this particular case, there's no fancy number to throw in there to tell us what's gone away in that 35 seconds or 17.5 seconds. So we're just going to say rate is inverse to time. So for 0.2 molar I minus, the mean time is 35 seconds, so the rate is 1 over that, 0.0029 per second, and for the 0.4, it's going to be rate is 1 over 17.5, which is 0.0057 per second.